All right. Today I would like to, talk about a project that I worked on for a few years as a side project. And just to start with the gist of it all, it's a re-implementation of TeX 82 in Rust. And I would like to give you just a short introduction why I even started doing that, how I proceeded working on this, some difficulties that I encountered rewriting this code, and what I have today and the outlook. But before I get to anything else, maybe just a little bit about myself. I don't really, I'm not an expert in tech. I work as a researcher in cryptography at the Technical University of Denmark. And so for me, this whole project was my first real encounter with low-level tech. So I've written, of course, as a researcher in natural sciences, I've worked with LaTeX, I've written my thesis in it, but I didn't really know how it worked on the basic level. Neither am I really an expert in Rust, so I've dabbled a little bit with the language before, but I didn't quite know it that well. So both of these are not as true anymore as they were at the start of the project. So I've learned quite a bit about both of these languages. So why I started, I recently had moved back from industry where I worked as a programmer to academia, and I was afraid I would miss the programming. So I was looking for a medium-sized programming side project. And yes, there's a little bit of naivety. I was a little bit naive about the whole process, I imagine. And I also wanted to gain some interest, some familiarity with Rust. So my first inclination was to write some sort of parser. And so I was looking at different languages. I was considering writing a PDF parser, but I heard that is very complicated, so I didn't do that. And because I was just moving back to academia, I was working with LaTeX again, and then I thought, oh, it might be fun to write a parser for LaTeX. While I was looking for a grammar or some description of it, I stumbled upon this file, tech.pdf, that you can get when you run a tech in your command line. And I found this beautifully documented code of TeX itself, and I thought, oh, this is nice. I can just, try to rewrite that in Rust. That might be a fun project. So my initial motivation when I started this project was how well can it even be translated to a modern programming language? So I knew, of course, of the reputation of the code that is basically almost bug-free. And so I expected that it might be nice, so it might fit well to some of the modern ideas that we have in programming languages. So in particular, I was trying to figure out whether I can rewrite it in idiomatic code. At the same time, I wanted to figure out whether it might help make the code easier to understand by utilizing more structure in the code, using stronger types and methods on data and stuff like that. And a bit naively, I also thought maybe the performance could be improved. I suppose the majority of you knows quite a bit about TeX, but just to give a very brief summary. So TeX 82 is still today the base of TeX engines. And was written in this literal programming language web, which compiles essentially to Pascal. And if you study the code, you can see that it has been written with really great care to use the absolute minimal memory, which was essential to run on the computers of that day and age. At the same time, it tries its utmost to be portable. So I'm not a computer science historian, but I understand there were many more operating systems and machines at the time. So it has no external dependencies. It makes minimal assumptions on the facilities that the operating system provides. and it sticks to only a subset of Pascal. So there were different dialects of Pascal with differing facilities, maybe some string facilities, but it sticks only with that which could be reasonably assumed of most Pascal compilers. So because of these constraints, there are a few things that are a little bit different from how you might write code today. So all memory is statically allocated. There's some very large arrays that are then used basically manually as dynamic memory. There is a lot of global variables that are used for all different kinds of purposes. Constant strings in the code are handled via a pool file. So they basically each constant string is represented as an index into the pool file, so that if you have repeated strings, then you can save some memory. And dynamic strings are stored in a single buffer. And there's lots of go-to statements, which is a little bit of an issue for languages that don't provide go-to statements. So Rust is a fairly new programming language. It's quite, I suppose it's quite popular these days. It roughly, I think, so my understanding of it is that it's roughly in the same corner as C++. So it's very fast. It is, you don't pay for stuff that you don't use. So you have very much control about execution time and about memory layout. It provides a lot of type safety, so you don't really encounter bugs very easily where you accidentally convert one type to another. And a big feature nowadays is that it has a system that allows it to be memory safe. So you never, if you have a conforming program, you can never encounter a case where you access invalid memory. So with regards to how well it's suited to translate web translate web from it, it is an imperative language, which is good because Pascal is imperative, and so in that sense it's easy to do. It has a macro facility, so because web uses macros quite extensively, that helps you to create the Rust code, and if you want to stay with at least with a semi-fast and maybe a controlled memory usage, it allows you to do that as well. On the downside, though, it does not allow mutable global state. So this is part of the idea of ensuring that you never access invalid memory, and that, of course, is a problem if you have lots of global variables. There is no go-to statement, and you don't. For the same reason, you also don't allow transmuting of memory. There is, though, an escape hatch, because this language is targeted at implementing low-level programs. You sometimes need to be able to do things that that can be unsafe. So the idea that it works is that you label those parts of the code where you do something that could be invalid with an unsafe word, and then you just make by manual inspection and reasoning, you make very sure that that part is correct. And in that way, you can have a mixture of safe code that is guaranteed by the language to be safe and unsafe parts that are humanly assured to be safe. So, and with this escape hatch, it was possible to do a first translation. So, while I started with this project, I learned that there were other attempts of doing it, and I realized that it might be a bit tricky to do. So I decided for the following approach, which I called ship of Theseus approach, where I start with a translation that is as close to the original as possible to avoid introducing errors that are very, very difficult to fix later. So with this initial, so I did this initial translation. Then I used the trip test. So if you don't know the trip test, it's one TeX file basically that is extremely convoluted and hits all the weird corner cases. And you need to ensure that that file gets compiled exactly if you want to make sure that the TeX implementation is correct. And then my hope was to make the code more idiomatic in a step-by-step fashion. So the things that I was hoping to improve within in this process was to use the actual dynamic memory that comes with the language provided. So that you don't have to have these static arrays, and that allows you to get rid of some constraints. You can easily grow the memory and adapt it to the usage of your TeX files. Then to utilize the built-in data structures such as hash tables, dynamic arrays, and other things, and just use the language and the facilities that this language provides to make the code, the programming easier, and the code maybe easier to read as well. And in the same fashion to use richer types. So, for example, Rust comes with an enumeration type. So if you have a finite set of states that you can be, and you can use this enumeration type to list these states, and you can be sure that you can never have a state that is outside of the set. And at the same time, the compiler can help you to make sure, if you're trying to cover all cases, that you indeed covered all cases. I also, and this is something I did initially, I got rid of the string pool because that is actually very, very difficult, even with the initial implementation, to include. So I just started with static strings. So inevitably, there were a lot of challenges. So I wrote this the initial translation. I did it manually, and this is definitely not the best use of time. I think it would have been much, much faster just to try to write a transpiler in the C-Web style, maybe. But there's a certain zen to just implementing it, and I also wanted to get a first read of the code. So while I was implementing it, I already had an idea of the layout of the different parts, even without understanding what it was actually doing in detail. So this manual translation, of course, created some bugs because somewhere you forgot maybe a line, or had a small spelling mistake. So I worked on this manual translation then to get it to compile with a trip test, and that is also not an easy thing because the trip test is not well documented, I would say, and especially if you don't know TeX, it's very, very difficult to wrap your head around what's going on. But eventually, I managed to get that going. And so then I could proceed with changing out parts of the implementation. And that was also more difficult than I anticipated because there's lots of interdependencies between the different parts of TeX. Maybe if you've read the TeX book, you know of the mouth and the intestines and different parts, and you think, okay, maybe I can just do these individually, but there's lots of interrelations. And of course, at times, it's also difficult to understand the nuances of the code. So the code is really well documented, but not every decision has been documented, right? Sometimes you sit there and puzzle, and often the answer is, oh, you save a byte somewhere. Sometimes it's also just because I don't know TeX well enough, so I need to understand what it's actually supposed to be doing, and then I can understand the code. So this is an example this is the original Pascal code. So this is a function procedure that essentially deletes a linked list. So P is a pointer to the head of a singly linked list, and it deletes it from this array of a memory array. So if in the first run of translating that, it would look like the following Rust code, and as you can maybe see, if just close your eyes a little bit, it looks very similar, right? So you have this unsafe keyword initially at the function because almost every function uses some kind of global variables, so you needed that for basically all functions. And then you have the same variables, and it translates rather well. You have of course some changes. I don't think so it's not in this code, but in some codes I needed to have basically a go-to crutch, I call it sometimes, where you use a loop as to simulate a go-to statement. So a loop can have a label, and then you can break or you can continue to a specific label, and you can. It's a bit ugly, but it works sufficiently well for an initial translation. So as an example of interdependencies of these different parts of TeX, so when you read an input token, which is in some sense the first step that a program does, right? It starts with a line in a file, and it tries to understand the first token. So one thing it needs to know is what are the current category codes? Are we dealing with a single letter? Do we start with a control sequence? So it needs to know these current category codes, which themselves are, again, global variables that are bound by the semantic nest. So how deep are we nested? So there are scoping rules. You might cause an error. And that again depends on the global state. So this function might fail if you read the wrong token at a specific point in time of execution. This input routine might want to log to a file or write to standard out. And it also needs to access again a global variable. So for example, if you just finished a file, there's a certain variable that you can set where you can manually verify each line you read in. And so there's really just a lot of interdependency. And also if you're basically in a table, maybe the alignment state can change. And then again, if you log an error, you need to know about what the current input stack is, because you might interactively add or delete from the input stack. And you need to know current definition of certain control sequences if you print the current context. So it wasn't really easy, or it's not quite feasible to really separate parts. And so what I ended up having in the end was 3 entities that are semi-global objects. So one is the logger, which is responsible for interaction with the user and printing to the log file and standard out. Then there is the EQTB, and this is something that comes from the original implementation. It's a table of equivalence, which is basically the store for all variables and their current state. And then there's the scanner, which is responsible for scanning input, for scanning the next token and maybe expanding it. So, and because these all have interdependencies, you often end up with methods that have a function signature like this one. So where you have, so this is just a small function that ensures that a list is empty when in math mode. So it takes the current list, but then you need to pass the scanner and the EQTB and the logger, because you might need to print an error or various different things. So that was unfortunately not possible to get rid of these. So it doesn't, it wasn't quite possible as I had hoped to separate concerns as much as I wanted to. So what is the current state of this project? So the implementation passes the trip test with a very minor caveat. There is one line that appears in a different space, just because I changed the order of 2 things. It does produce binary identical output, so I verified that on my computer with my TeX Live installation. So when you adapt the comment strings, the version strings, and the timestamp to the exact same time as then you can get the binary identical output. So the code no longer uses global variables, and there's no unsafe code left in it. And I removed most limits, built-in limits of the original TeX implementation. So there is no limit on the number of control sequences or the number of registers or the number of strings. But I did leave some in because they're actually helpful when you're programming. For example, if you have a file that includes itself, you really wanted to stop after a fixed number of steps and not before you run out of memory, right? So I left a few of those in. And in the spirit of the original implementation, I wanted to avoid any external dependencies. So it's a self-contained contained program. So there's a few buts. I was a bit naive about the performance initially. I was kind of hoping, with a modern compiler and whatnot, maybe some stuff gets faster. It did not. So it's currently slower by a factor of roughly 2. I don't quite know where this is lost. I have some suspicions, but I imagine it's possible to get closer in any case to the original speed. But I did get an appreciation for how well the original code was written. That even today, it's really fast, I think. So it doesn't have any integration with kpathia, if that's how you pronounce it. There's only hard-coded directories, so you can't quite use it as a normal TeX installation. You need to put the font files and the input files in very specific directories. There's no working timestamps, which is because I wanted to avoid adding an external dependencies, and implementing time facilities is quite cumbersome. So at the moment, it's I think it's always 1776 for the program. It's only implemented for Linux because that's what I run personally. There's no PDF output, and there's no epsilon TeX extensions, and I did not write a lot of documentation for it, so most parts of the code just reference the corresponding sections of the original TeX implementation. So if you want to check it out, you can find it on GitHub under this link, and yeah, thanks for listening.
Are there any questions for TUG? Yes.
My question is, I found when I wrote it from web to CWeb that my translation invalidated most of TeX documentation. So the code was not longer matching the documentation that was in the CWeb file. You just reference the original documentation. How do you document the differences?
Yeah, that's a good question. So the answer is probably I don't. So far I've been working with it for myself, and it's a side project, so I focused on the stuff that is fun, and documentation writing is not always fun. So some parts did change considerably, and there's not a very good match between those, and others are almost literal translations still. So it really depends on where in the code it is, but it's not indicated in the code when it changed a lot.
Yeah, this is a hard part. When I started, I thought the documentation is the easy part, but it's a hard part.
But important for others.
I'm curious about were you able to leverage the Rust type system to somehow catch many bugs? And I was a bit disappointed to see that this was a pure rewrite, meaning the interdependencies were kept, which I imagine would essentially keep you from using most of the pros of using a type-safe and stronger type language.
So there are, let me think. So I know, I looked a little bit into implementing eTeX, and I know I think there's a small bug, for example, where I can see, because I don't use global variables, that it doesn't pass, the implementation doesn't set a certain global state, which needs to be passed in the function signature that I have. But it's minor, really. So, I mean, TeX is really well written, so it's not easy to find bugs in it. So I think the main purpose of these is for myself, as it was for myself when rewriting it, and I think it can be utilized if you extend it, right? So let's say you want to add a new node type, right? You need to. There's many places where you would need to check that you handle those node types well, and I think that's where probably these types might be useful.
A question from Luigi Scarsa through YouTube chat. He says, nice talk. I'm a little surprised by the 2 times slowdown. It might be interesting to transpile a subset of the LaTeX base code into Rust, maintaining the code's recognizability. We need it to be in sync with the PDF code base.
So I didn't quite get the question.
It's maybe a question about the slowdown and the comment that they probably need to do something with LaTeX, because in LaTeX you have a lot of Lua, and it would be probably interesting to see what happens when you do something with Rust.
Yeah, so I can say so one fundamental thing that changed is that in the original implementation, all lists are basically linked lists. and I changed that to be dynamic arrays. So I now have, so that can be an advantage at times when you want to have just jump into to a specific position in the array, but as a disadvantage when you just want to cut and slice these arrays. So I think that because the original implementation was of course tailored to these linked lists, there might be some efficiency loss in that regard. And I think this continuous parsing of these global structures that are probably not optimized away can be another slowdown of this code. But that's only guesses.
I think the last question.
You mentioned K-path-C, or Carl's path searching algorithm I discovered lately. If you can use the shell in Rust, you could call KPSE, which?
Yes, yes.
In order to just get rid of the static files for the moment. I don't know if you want to continue this project.
Yeah, I did actually try that out, and that works well. I mean, it's a bit slower because you get some, well, you call it again and again, but it's, I mean, you don't call it that often. So I think it works for practice. That's a nice hack to very quickly, get integration with that. Yes.
And also, if you could static link, for example, K-path-C lib, you could do it natively, I guess, or with more performance?
I imagine, to be honest, I have not looked into it, so I don't quite know how complicated or easy it would be.
Okay, thank you.
Okay, thank you, Tyge, for your talk.